Hey, what's up, guys? This is Chung here. So today, LeetCode 1764. Form array by concatenating subarrays of another array. So you're given like a 2D integer array groups of length n, and you're also given like an integer array nums here. So you need to choose like n disjoint subarrays from the array nums, such that the ith subarray is equal to the group's I. And you need to return true if you can do it, otherwise false. So basically what does it mean? It means that you're given like a longer, basically a pretty long like nums here, and another like bunch of like array of groups groups of array. So you need to find some subset, right, from this nums, so that you can basically find a match for those for each of the group uh, within a sequence, right? So for example, this one, right, we have this kind of numbers, and we can find, so for one, minus one, minus one, this is the match we can find. And then we have another one here. And remember, so basically those two matches cannot be overlapping to each other. That's why we call it disjoint, right? That's why this one is true. And for the second one here, we have 10 minus 1, right? Because 10 minus 1 is right here. But the 1, 2, 3, 4 is not, because it's the sequence, basically the order matters, right? So whenever, basically we have to find the first one first, and then we can try to match the second one. So, and after matching the first one, we already reached the end of this nums here. That's why we'll just return false. Okay, and here are like some more examples here. And the constraints is like 10 to the power of 3. Okay, and then that's the range of the numbers here. So, I mean, for this problem, I think brute force way, not a brute force way. I mean, naive approach is simply we just try to match this kind of groups one by one, right? And whenever we find a match, right? Whenever we find a match, we will basically move to the recursive function, a DFS call, right? And then we'll try to match the next one until we have reached the end. We either have matched all the groups, that's when we'll return true, or we have reached the end of the nums, which means we need to return false. Okay, right. Basically, that's the basic idea here. And so for this problem, that's the basic idea. But to do this string match or the array match here, we can simply do a brute force like array equals to array, or there's another like a more efficient way. It's called KMP, right? So basically today I will be doing the naive solutions, and then I will also implement the KMP. Basically, the KMP will change the O of m times n time complexity to O of m plus n. All right, so let's try to implement the first one. So for me, I'm using this kind of DFS approach. Basically, we have n equals to length of the groups, right? So that's a total groups we need to match, and then for the m equals to the length of the target, the nums. Okay, and then we have the DFS, right? So we have the DFS. So we have a group index, okay, and then I have a num index. So that's the two things I'll be maintaining in this function here. And then in the end, I simply return DFS 0 and 0. Cool. So, and the base case, right? If the group index equals to the n, it means that we have matched all the groups. So we just need to return true here, right? Else, not else. So if the num index is equal to m, which means that we have reached the end of this array, but we haven't matched all the groups. That's when we need to return false. Okay. Otherwise, right? So we have a current group equals to groups dot group index, right? And then for current numbers, and since a brute force way is that we just need to iterate all the numbers, right, from all the index from this num index until the end, until m here, right? But then to be able to form the current numbers, we have to basically do a array slicing. That'll be another layer of the time n of n time complexity. So for me, I'm just using a dequeue here so that I can only append to the end and pop from the left, so that I can basically update the current nums in the O1 time. So which means that first I'm going to start from the num index, right, and now stop at m. Okay, so the current nums dot at the beginning, I'll just append this one to the nums dot I, which will be the current numbers, right? And if the length of the current numbers is greater than the length of the current group, right? And then we know, okay, we need to pop, right? Because in order to make to find a match, the length has to be the same. If the current one is greater than the current group, we simply do a pop left, and then we just do this. If the current group equals to current numbers, right? I think for this one, since we're defining as a dequeue, we have to convert it back to the list. So if they're the same, right, and then we can just simply return this one. We can return the DFS. Basically, we have find a match, and we just need to throw this the question to the next layer, which is the index group index plus one and the I plus one. So this one is easy to understand. The I plus one means that we have to start from I plus one because the group has to be disjoint, which means that the remaining part is only from I plus one to m. Okay, and here actually, so we do a return. We didn't do something like this. Okay, let me finish this one. So, and if none of them matches, we simply return false, right? But keep in mind here, so we do this one. We didn't do something like this. I mean, if this one is this one, then we return true, something like this. So what does this one? If we change it to this way, it means that let's say if we have multiple match, if we have multiple match for the same group here, we'll try all the possible matches, and then we'll return anyone who give us a true here. Otherwise, if this one is a false, basically we'll keep try a different maybe the next match. So the reason we didn't do this one is because this is here is kind of like a greedy idea here, so the earlier we can stop the current match, I mean the bigger chance we can find like the match for all the groups, right? Because let's say we have this is a number, right? Let's say we have the current groups is 3, so let's say we find like a match from here to here, and then let's say if this one didn't give us like a true return. Let's say there's a match from here to here. Okay, so if this one didn't give us a true, right? So this one will definitely not give us a true either, because the earlier we stop the current one, I mean the more numbers, the more like numbers we have for the remaining groups, right? So basically that's why as long as we can find the first match, we can simply return that value directly, because we know that this will guarantee that can definitely tell us if we can return a true or false. Okay, so I think that's it. So if I run the code here, oh, sure. Yeah. Okay, submit. Yep, so it's passed, right? And so for the time complexity, right? I mean, as you guys can see, so here we have a range, right? So we have a range of, you can call it like an n, right? Because the constraints for this m and n, they are the same. So we have a n here, and then for the comparison here, right? We have basically we have an n square here, because for the compare the list, we have to compare them one by one. That's why we have n square. And then how many times we're gonna we're gonna basically do this DFS, right? So ideally, I mean, the worst case scenario, it should be like n cube, right? I mean, the n square times another n. But the reality is that every time when we have matched a group here, the search range for the next DFS will be smaller. Basically, it will not be exactly n. It will be smaller than n, right? So that's why I think the time complexity for this one is going to be between n cube n squared to n cube. So I'm not quite sure about what is the exact time complexity, but it should be in the range of these two here. Yeah. So basically that's the basic idea. And so let's talk about KMP, right? So for those who don't know what KMP is, basically it's an algorithm to find us like a pattern within a string. So to find, let's say we have a string, right? Let's say we have a string with this one, right? And then we have a pattern, a substring. If we want to know if there's a match for this pattern in this string, right? So the brutal force way is that basically we loop through all the indexes, right? And then we do a comparison, which means that let's say this is m, this is the length of n, so the time complexity obviously is going to be m times n, right? But for the KMP algorithm, we can basically improve this one from m times n to m plus n. Okay, so how does KMP works? I'll briefly talk about KMP here, and for the entire complete explanations, I have like another video to explain this KMP algorithm. I'll post it into the description of this video here. So basically, the way the KMP works is that we're gonna build like a helper array for these patterns. Basically, it's gonna be a longest. So the helper array called the longest prefix as suffix. Okay. Yeah, so which means that if we can build this longest prefix as suffix, so whenever we try to find basically we try to find the match for this one. So basically it works the way it works that we're gonna have like an I here for the source, and then we have a J index for the patterns. Every time, as long as they're the same, basically both I and J will keep moving forward. Okay. And whenever there's a mismatch, let's say if the I is here and the J is here, and if there's a mismatch for I and J, right? Basically, we'll move J back to like a previously state, so that the I and J can keep moving forward. Basically, and we can still comparing only this I and J index for each of the move. So, and how can we, and let's say if the I and J are different, how can we know which place this J should move back? That's when we need to use this longest prefix as suffix. Basically, with these values here, we know with this helper array here, and then we'll know basically where we should move this J back to this certain location. Yeah. So I'm not going to talk about that here, but I'll post that video here later on. So okay, let's try to implement these things here. We have DFS. Okay, so to do that, like I said, we need to build the longest prefix as suffix helper functions. So for the group, because the group is the pattern we're trying to match here. Okay, so the way it works is that we have a group here, and then LPS, right? The longest prefix as suffix. So at the beginning, the length for each of the element is 0, and then we throw n, and then we have a j equal to 0. Okay, so I'll just keep typing here for I in range of 1 plus n, while j is greater than 0, and the group of I is not equal to group of j. If they're not the same, right, they'll basically will update j with LPS j in minus 1. And then if the group I equal to the group j, basically the LPS I equals to j plus 1, and then j will increase by 1. And then in the end, we return the LPS. Okay, so that's how we build this helper like function here. And let's see what else. So here, we have a current group, and we can just change this one to the LPS, right? So LPS is going to be the helper functions we just created, PS of the current group, right? So that's that. And then to match the these things, we're going to have like the j equal to 0. So here we don't need to do this kind of match. So I can just do this. Basically, while j is greater than 0 and nums I is not equal to the current group of j, right? So if they're not the same, then like I said, j will be falling back to the previously value, right? And then if the nums I is equal to the current group, right, then j we simply increase the j, because the I is already increasing, right? Because we have a for loop here. So whenever they're the same, we move both an I, j, and j forward. Okay, and so the condition to know if we have find a match is that when the j equal to the length of the current group. Okay, so basically this j means that how many characters we have matched so far for this pattern, which is the current group here. And whenever the j has reached the end of it, we know, okay, we have find a match for the entire group, and that's when we need to call the DFS, right? Current group index plus 1, and then the I plus 1. Yeah, yeah. Basically, that's the change we need to make here. And if I run the code here, okay, return code, run code range. Oh, range. Okay, accept it. Yeah, so it works. This one is even slower than the other one. Yeah, they're basically has the pretty exact almost the same speed, but regardless, right? Regardless, as you guys can see here, so now for each of the DFS here, so to build this LPS here, we have a for loop here, right? So that's the an n here, right? So we have an n here, and then for this one, for the for loop here, as you guys can see here, now we only need to do like this kind of this range here. There's no nested for loop here, and so this while loop here, even though we have while loop here, this one has a very limited time complexity, because the nature we build this LPS, so this one we can consider it as O1 here, and then as you guys can see, we don't have like a array comparison. All we have is kind of like a in ladder a single ladder comparison. This is also O1. So that's why the total time complexity within the DFS is going to be a n plus n, right? Because we have actually n plus m. Let's say we have m here, right? And then for the total time complexity for this solution, maybe like times another n here, because we have basically another layer of the DFS, right? Yep. Basically, that's how this problem works, and how we can use the KMP to speed up, to improve the time complexity for this one. And yeah, I think I'll just stop here. And thank you for watching this video, guys. Stay tuned. See you guys soon. Bye bye.